Hello people, today we are going to work on 5.7, interpreting graphs of linear functions. And we're basically just going to finish this chapter up. We're so close. So, any of a graph of a line that is not vertical, so a vertical line would just be straight up and down, represents a function. So a straight line that's not just vertical, they are functions. We call these linear functions. And we can use intercepts to describe the graphs of these linear functions because these intercepts are often really interesting points. So a horizontal intercept, remember horizontal goes this way, kind of like left and right. Sometimes we might call that an x-intercept. Because guess what? A horizontal intercept will be on the x-axis. So horizontal point is the point where a graph crosses, or touches at least, the x-axis. So if I were to draw myself a little picture, if this is my graph, this would be my x-intercept, or my y-intercept, or sorry, my horizontal intercept. So x-intercept or horizontal intercept, say the same thing. The vertical intercept, remember vertical goes up and down. Sometimes we call this the y-intercept. It is the point where a graph crosses, or at least touches, the y-axis. So y-axis is this vertical one. If this is my graph, this would be my y-intercept. Now I should really put arrows on this because in my little examples here, my graphs go off forever. So it's where it crosses the y-intercept. Now these are typically really interesting points, especially if we're looking at like a certain context. So here's an example right here. I have two intercepts. Where I cross the y-axis over here, that is my y-intercept. Sometimes I just write down y-int because I'm lazy, and I'll say 0, 5. Or I could say y-int equals 5. Because the 0 part of this is kind of built into the idea. Y-intercept, it's where I cross the y-axis. X would be 0 on that line, so the y part is just 5. This is my x-intercept, x-int 0, 2, or x-int equals 2. And then the 0 part of it's kind of just built in, because if I'm on the x-axis, then my y value must be 0, because I'm not going up or down or anything. Okay, so that's kind of what we're starting off with here. Now let's try and use it in a couple different ways. So we can use intercepts to graph a function. Yesterday what we did was we took this, we made a table of values, and then we graphed each point and then connected with a line and arrows and all that. That's a great way to graph a line. Another way to graph a line is to find the x-intercept, the y-intercept, and connect them with a line. This really only works with linear functions, because if it has some kind of curve in it, like we'll talk about next year, we won't be able to just connect a straight line. But for this year, it's a great method. So let's go ahead and find our x-intercept first. Now reminder, if we're talking about an x-intercept, we're on the x-axis. The y value will always be 0. So I'm just going to put in brackets here, y equals 0. So when I take a look at my function here, y equals 2x minus 6, I'm going to substitute y equals 0 in for 2x. Sorry, in for y, and we're going to solve for that x value. Now we're substituting it in because I know that y will equal 0 for my x-intercept, and I want to figure out what x is. So 0 equals 2x minus 6. And let's try and get this x value by itself. So we're going to do the opposite of what's already happening. So this is plus 6, so minus 6, we're going to add 6 to both sides. And whenever we do it to one side, we always have to do the other because we have to keep this equation balanced. So 6 equals 2x. Now this is 2 times x, so we're going to divide both sides by 2. 2 divided by 2 is 1, that's great, it just cancels out. On the left we get 6 divided by 2 is 3, so x equals 3. So I have a point, 3, 0. When y is 0, x is 3, and I have an x-intercept. Let's put that on our graph over here. So 3 to the right and nothing up, we're right on the x-axis. There we go. That's my first point. Now let's find our y-intercept. When we have a y-intercept, it will be on the y-axis, so x will be 0. So I'm going to start this again here. Y equals 2x minus 6, and this time wherever I see x, I'm going to substitute in a 0. So y equals 2 times 0 minus 6. 2 times 0 is just 0, so y equals 0 minus 6, y equals negative 6. So I have a point here, 0, negative 6. When x value is 0, y is negative 6, that will be on my y-axis. And there's my y-intercept. Now, because this is a linear function, I know it's a linear function because it's not squared or anything like that. There's a constant rate of change. Because it's a linear function, I can connect these two dots with a beautiful, nice straight line. And I wish I had a ruler here. I'm going to try and do this really nicely, but you will hopefully be able to find a ruler. Oh, there we go. I do need to put arrows on it because this thing could go on forever. Like I could find what would y be if x was 1,000, and you'd be able to figure it out, or 1,000,000, or 2,000,000, or whatever. So this thing goes on and on forever. And let's label it. Y equals 2x minus 6. And just for fun too, I'm going to label my intercepts because they were kind of special points in this question. So there we go. I just graphed a function just by finding the two intercepts and drawing a line through them. That's another way that you can graph a function in this course. All right, let's continue on. All right, the horizontal and vertical intercepts of a graph have meaning. Like when a graph like this, there was no context to this question. It was just, hey, here's a graph, here's a line, graph it. But when we're talking about like a situation or like a story behind the graph, they have meaning. They mean something specific. We need to be able to describe what they represent in the context of the graph. Like what is their special meaning? Okay, so let's try this one right here. This graph shows the height of a burning candle, how the height of a burning candle changes with time. Determine the horizontal vertical intercepts and determine what they represent. So let's start off with the x-intercept, because why not? So I want to figure out, where does my graph cross the x-axis, or where does it touch the x-axis? Right there. My x value is between 40 and 50, so I would say at 45, 0. And what does that represent? Maybe you can hear my dog in the background, sorry about that. What does that represent? Well, in the context of this graph, it kind of looks like this is how tall the candle is, and over time it just gets burned down until eventually it's 0 centimeters tall. It takes 45 minutes for this candle to burn down to nothing. So the interesting thing about this is that it takes 45 minutes for a candle to fully burn down into nothing. That's what we're trying to, that's what's interesting about this one. So describe what it represents. It would say it takes a total time. It takes 45 minutes total. Notice I use some units in here. 45 minutes total for a candle to completely burn out. Burn, when we say burn down, to nothing. That's my x-intercept. Now my y-intercept. That's on the y-axis, that's over here. Let's try and guess what that will be. My graph's not as nice as yours because I just used my home printer here. Let's see, that's 8. So up here would be 10. So I would say we're at 9 hours there. So 0, 9. So we're not 9 hours, 9 centimeters. And let's try and figure out what that means in the context of this question. At time 0, before you really started burning it, or like the moment you started burning it, my candle was 9 centimeters tall. So that's the height of a candle before you started burning it. Like that's the original height of the candle. And that's probably the interesting part about this. So the original height of the candle was 9 centimeters. That tells us a lot of information. This graph tells us a lot of information, and the x and y intercepts actually tell us like a lot about the story that we didn't know just off of these couple of words. What is the domain and range of this function? Now, this is where we have to think a little bit about what could happen in this graph that they don't necessarily show us. Would it be reasonable, so this is my graph, that's what they showed me. Would it be reasonable for this graph to continue on in this direction, up and to the left? And I want you to think about what that would be. That would be, let's say, up to negative 45 minutes. Can you go back in time 45 minutes? No, that doesn't really make a ton of sense. So it really doesn't make sense for this to go back and to the left, because that doesn't make sense. And it doesn't make sense for this to go down and to the right either, because then your candle would be burning like into the table, and that would probably not be a great thing for your house. So the domain here is very specifically from 0 to 45, and it cannot go further than that in the context of this question. So domain, I'm going to use interval notation because that's what I enjoy using. And let's think about the type of brackets we're going to use. Do we hit 45 minutes? Yes, that is a closed dot, so it's a closed bracket. Do we hit 0 minutes? Yes, there was a time that we started the timer. We include that. Range from 0 centimeters up to 9 centimeters. And again, that's included here because we will start at 9. There will be eventually nothing at all left. All the wax will be burnt off, and we'll have 0 centimeters left. So it's always goes from smallest to biggest, right? What is the rate of change? Okay, we talked about this yesterday. I'm too lazy to write it all out, so I just write ROC, rate of change. And when we look at rate of change, we usually look at rise divided by run. So rise is how far in the y direction have we changed, and rise and run is how far in the x direction have we changed. So from this point to the end, I went from 9 centimeters to 0. That will be negative 9 centimeters. It's going down by 9 centimeters. So it's really important we have that negative in there. And it's important we have the units too, because that will be part of our answer, and it'll help us figure out what we need. Now run. We went from 0 to 45 minutes, and time is positive here because I'm increasing in time. So positive 45 minutes. Now these are really nice numbers to reduce, so we should definitely reduce this. 9 over 45, I think we could divide both of those by 9. So negative 1 centimeter per 5 minutes. Or another way of just writing it would be negative 1 over 5 centimeter per minute. And I ran out of space on my paper there. Or if I had a calculator, negative 0.2 centimeter per minute. Now, what this means is every minute we're losing 0.2 of a centimeter of our candle. Geez. All right, let's take a look at these guys. Which graph has a rate of change of -5 and a vertical intercept of 100? Justify your answer. So a vertical intercept is on the y-axis. So here's my y-axis, and I do have a vertical intercept of 100. So far this is in the running. How about this one? This one also has a y-intercept of 100. So those didn't really help me. Now, what might help me next is the rate of change of -5. Whenever I have a negative rate of change, it will be going down. Whenever I have a positive rate of change, I will be going up. And I'm talking when I look from left to right, it moves up. So if I start here, this is a mountain I have to climb up. If I start on the left, this would be like a slide, I'm going down. Okay? So which one of these has a negative rate of change? This one. I didn't really even need to calculate that it's -5. I can tell that one's negative, that one's positive. And there we go. All right, let's see what else we have here. Let's solve some problems. All right, solve some problems. It's a little bit more contextual now. This graph shows the publishing cost of a school yearbook at FRC. Explain why the points are not joined with a line. Now, we talked about this quite a while ago. We talked about when there are individual points like this, we call them discrete. If it was joined by a line like this one, we would call that continuous. And what I want to think to myself is, would it be reasonable to throw a ton of little dots in the middle there? So many little dots that they would kind of connect to each other and join a line. So can I buy one yearbook and have it printed? I mean, maybe. Sometimes publishing companies make you buy a certain number of them because it's not really worth your while otherwise. So maybe you could buy one yearbook, but could you buy half of a yearbook and have that printed? No, because they'd be like, what do you mean you want me to print half of it? Like, which half? You can't print 0.1 of a yearbook. That makes no sense. So no, oh yeah, it should not be joined with a line because you cannot print or publish or whatever, print any increment of a yearbook order. Any increment of a yearbook, that's all right. So like I cannot print half a yearbook. That doesn't make sense. So I cannot join these points of the line. These points are discrete. All right, now let's try and read this graph a little bit and to find out some stuff. FRC has a budget of $3,500. What is the maximum number of yearbooks that can be printed? Okay, so $3,500, that'll be on our cost. That should be right between our 3,000 and 5,000. And I want to figure out how many yearbooks that could get me. Looks like there's a dot on our line right there. And let's figure out how many that is. So I'm just going to go straight down. That's 150 yearbooks. These questions, it's really important we use units because a different unit would mean something totally different, wouldn't it? And of course we could print less than 150 yearbooks. I could print like 100 and I would just be under budget, but then some people wouldn't get one. If you wanted to print 200 yearbooks, what would be the cost? Okay, so up from 200, your graph is a little nicer than mine because my printer doesn't work great. There's 200 and I want to know the cost. So I'm just going to go straight to the left to see how much. And it's a little bit off my graph here, but I think the next number would be 5,000. So we're between 4,000 and 5,000. I'm going to call that $4,500. And of course more yearbooks, it's going to cost more. That's reasonable. So it's always good to just kind of think about my answer and make sure that it still makes sense. Okay, let's try this one here. This graph shows the total cost of a house call by an electrician for up to 6 hours of work. Explain the meaning of any intercepts. Okay, let's look at which intercepts we have here, because I think we only have one. I have an intercept right here where my graph touches the y-axis. So this is a y-intercept at, I think that's about halfway, 0 and 120. So I'm going to call that x is 0, y is 60. What this is saying here is the electrician shows up to my house, does 0 hours of work, and I'm going to pay him $60 right now. That's actually pretty common with things like electricians and plumbers and things like that, because we call it a base price. And basically it covers their time and effort to get over to your house. So the second they show up, you pay them $60. And then however long it takes them, you pay them more for every hour that they're there. And yeah, it kind of covers just like the service call. Like they had to, let's say it was in the middle of the night, your water's out, you call them, they have to get up in the middle of the night, get in their vehicle and drive over. So you pay that plumber $60 just to show up. So what it means here, explaining the meaning, it means there is a base price of $60 where no number of hours have been worked yet. Yeah, I'm just going to say that. That's good enough. Determine the rate of change. Now, to find rate of change, we know how to do this. We basically take any 2 points on this graph. We look at the change in y and the change in x. Now, I typically use like the first point and the last point, but you can use any. So let's just prove to ourselves that this works by using these 2 points. And if you'd like to, use any other 2 points, like maybe the first one and the last one, to show you that it works. Basically averages it out. Okay, so rise. So I want to go from here, from this first point to the second one, how much do we go up by? So rise, we start at 60 and go up to, let's see, what's halfway between 120 and 240? I'm thinking that'll be 180. So we go from 60 to 180. I'm just going to write my thoughts down here. 180 minus 60, because that'll give us how much we go up by. And run. We go from 0 hours to 3 hours. So 3 minus 0, because yeah, it's only 3 hours that have elapsed. Let's see here. That'll be 120, I forgot to put my units on here, but dollars over 3 hours. And when we can reduce something, we definitely should. So 120 divided by 3 is $40 an hour. So once this electrician shows up, you pay them $60 to show up. Every hour after that, you'll be paying them $40 for an hour. All right. The electrician estimates he can complete the job in 2 hours. How much would you expect to pay him? Okay, let's hope my graph works out nice enough because it's hard to read. So here's 2 hours. There's my dot. And you know what? You're going to have to read it on your own here because I don't think mine's very good, but let's see if you can read it on yours. It looks like it's a little bit above 120, but I'm not 100% sure that it should be. Let's just take a look at my graph. Yeah, it's a little bit above 120. So let's see. Let's call it like about $150. I'm kind of guesstimating. It does say approximately because it's hard to read exactly off the graph. But I know it's going to be between 120 and 180 because this one over here was 180 and I'm definitely not that high. I'm going to say about 150. The electrician charges you $180 to complete the job. How many hours did they work? Okay, well, I just drew a line there. 180 is 3 hours. And this is just us reading off the graph there. Alrighty, so give this a try. Let's see how it goes. And thank you.